Hello, everyone. I'm Aaron, and today I'll talk about our work on sum of squares lower bounds for densest k-subgraph. This is joint work with Chris Jones, Goutham Rajendran, and Jeff Xu. So in this talk, I'll first introduce the densest k-subgraph problem. I'll then describe the known upper bounds from the log density framework and a spectral algorithm. I'll then describe our sum of squares lower bound for densest k-subgraph, and I'll end by giving a taste of the technical analysis. So first, the densest k-subgraph problem. The densest k-subgraph problem is as follows. Given a graph G and a natural number k, find a subgraph H of G such that H has k vertices and H has as many edges as possible. So for example, for this graph G, if k equals 5, then the answer is the 5 vertices in the center, as there are 8 edges between these 5 vertices. So the densest k-subgraph is a central problem, and there's been a ton of work on it. So I'll only describe some of this prior work. In 2010, Bhaskara, Charikar, Shlampak, Feige, and Vijayaraghavan gave an O of n to the 1/4 plus epsilon approximation algorithm for any epsilon bigger than 0. In terms of lower bounds, so densest k-subgraph is NP hard to solve exactly, but to the best of our knowledge, a constant factor approximation has not been shown to be NP hard. That said, a constant factor approximation has been shown to be hard under other complexity theory assumptions. In 2017, Manarangzi showed that assuming the exponential time hypothesis, there is no n to the 1 over log n to the c approximation for some constant c bigger than 0. In terms of specific models, for all epsilon bigger than 0, logarithmic degree Shirali atoms cannot obtain an n to the 1/4 minus epsilon approximation, and n to the epsilon degree SOS cannot obtain an n to the 1/14 minus O of epsilon approximation. So in our work, we consider the following average case distinguishing variant of densest k-subgraph. We have parameters alpha, beta, gamma between 0 and 1, where beta is larger than gamma. For our random distribution, we just take GNP, where p equals n to the minus beta. For our planned distribution, we first choose a random set of vertices V of size approximately n to the alpha by including each vertex in V with probability k over n. Then for each pair of vertices U and V, such that U is not in V or V is not in V, we add an edge between U and V with probability P equals n to the minus beta. So this says that outside of V, the edge probability is still n to the minus beta. For each pair of vertices U and V in V, we add an edge between U and V with probability Q equals n to the minus gamma. Then the question is, can we distinguish these two distributions? So here's an illustration of the random plan distributions, where the random distribution again is GNP, and the plan distribution is roughly GNP plus GKQ. So now describe the upper bounds from the log density framework and a spectral algorithm. As I recall, our random distribution is GNP, and our plan distribution is roughly GNP plus GKQ. So a potential method for distinguishing between these two distributions is to show that there is a subgraph H such that with high probability, H does not appear in GNP, and with high probability, H does appear in GKQ. So it turns out that if gamma is less than alpha times beta, this method can distinguish with high probability between a GNP graph and a graph containing a GKQ subgraph. For example, if alpha is 1/2, beta is 1/2 plus epsilon, and gamma is 1/4 minus epsilon, then with high probability, GNP does not contain a copy of K5, but GKQ contains many copies of K5. So here's a rough calculation showing this. So we look at the expected number of copies of K5 in GNP. They're on the order of n to the 5th possible sets of 5 vertices. For each set of 5 vertices, the probability that it is a K5 is p to the 10th. So we get n to the 5 minus 10 beta, which is n to the minus 10 epsilon. Following similar logic, the expected number of copies of K5 in GKQ is on the order of k to the 5th times q to the 10th, which is equal to n to the 10 times epsilon, which is much bigger than 1. More generally, if we let H be a graph with x vertices and y edges, the expected number of copies of H in GNP is on the order of n to the x minus beta times y. The expected number of copies of H in GKQ is on the order of n to the alpha x minus gamma times y. So this method distinguishes with high probability between a GNP graph and a graph containing a GKQ subgraph if x minus beta times y is less than 0 and alpha times x minus gamma times y is bigger than 0. Multiplying the first equation by alpha and subtracting the second equation gives gamma minus alpha times beta times y is less than 0, which is possible if gamma is less than alpha times beta. So in fact, if alpha is less than alpha times beta, then there exist natural numbers x and y such that x minus beta times y is less than 0, and alpha times x minus gamma times y is bigger than 0. So the log density framework can solve this variant of densest k-subgraph. So this analysis works for the average case version of densest k-subgraph. But how about the worst case? So in order to construct an approximation algorithm for densest k-subgraph, which works for all graphs, Boconi et al. Use caterpillars. So a caterpillar consists of a path called the backbone and paths hanging off of the backbone called hairs, which they always take the hairs to have length 1. So Boconi et al. Use an RS caterpillar C, where S and R are natural numbers where S is bigger than R, and R and S are relatively prime. So this caterpillar has S minus R backbone vertices and R plus 1 hairs. Note that the total number of edges is S. So then what they do is they consider caterpillars with a fixed set of hairs V and choose R and S such that S minus R divided by S is between gamma over alpha and beta. So then the expected number of copies of C in GNP with the particular hairs V. So this is on the order of n to the S minus R times P to the S, as there are S minus R backbone vertices which can be chosen freely, and there are S edges. So this is n to the S minus R minus beta times S, which is less than 1. On the other hand, the expected number of copies of C in GKQ with the hairs V, if V is a subset of GNKQ, is on the order of K to the S minus R times Q times S, which is much larger than 1. So here's an example of the RS caterpillar where R equals 4 and S equals 7. So why do they use these RS caterpillars? So the key idea is that since the RS caterpillar C is a tree, there must be many copies of C in any dense subgraph H with K equals n to the alpha vertices and average degree D approximately equal to K times n to the minus gamma. And this implies that there must exist a set of hairs V such that there are many copies of C with hairs V. On the other hand, by carefully choosing the RS caterpillar C, they ensure that for GNP with high probability for all possible sets of hairs V, there are at most O of log n copies of C with hairs V. And then with a more intricate analysis, they obtain an approximation algorithm for any graph G, but this is more involved. So for details, see their paper. So this leads to a natural question. Is the log density framework optimal? So it turns out that for alpha, for alpha less than or equal to 1/2, the log density framework is conjectured to be optimal. But for alpha bigger than 1/2, a simple spectral algorithm does better. So to describe this algorithm, it's useful to introduce the following Fourier character chi-e on a possible edge E. So given a possible edge E equals UV, define the Fourier character chi-e so that it's equal to the square root of 1 minus P over P if E is in E of G, and it's equal to minus the square root of P over 1 minus P if E is not in E of G. So it's not hard to check that the expected value over GNP of chi-e is 0, and the expected value over GNP of chi-e squared is 1. So here's a quick calculation showing this. So the expected value over GNP of chi-e is P times the square root of 1 minus P over P minus 1 minus P times the square root of P over 1 minus P. And not hard to check that this cancels out and gives 0. The expected value over GNP of chi-e squared is P times 1 minus P over P plus 1 minus P times P divided by 1 minus P, which is equal to 1 minus P plus P, which equals 1. So now the spectral algorithm is as follows. So we'll let M be the matrix with entries Mij equals the square root of 1 minus P over P if Ij is in E of G, and Mij equals minus the square root of P over 1 minus P if Ij is not an edge of G, and we take the diagonal entries to be 0. So now M is a symmetric matrix whose entries above the diagonal are independent with mean 0 and variance 1. M is not quite a Wigner matrix because the moments of the distribution are not bounded, i.e. for k greater than or equal to 3, the expected value of mij to the kth power grows with n. Nevertheless, if beta is less than 1, then for input GNP with high probability, the norm of M is O of the square root of n. So now let's consider what the norm of M is for the planar distribution where there is a subset of vertices V of size approximately k with edge density n to the minus gamma. So let V be the vector with coordinates Vi equals 1 over the square root of the size of V if I is in V and Vi equals 0 otherwise. So note that this is a unit vector. So after V is chosen, the expected value of V transpose MV is the size of V minus 1 times the expected value over GKQ of chi-E. And then it's not hard to check that the expected value over GKQ of chi-E is equal to Q minus P over the square root of P times 1 minus P, which is approximately equal to n to the beta over 2 minus gamma, where the beta over 2 comes from the 1 over square root of P term, and the minus gamma comes from the Q in the numerator. So this means that the expected value of V transpose MV is approximately equal to n to the alpha plus beta over 2 minus gamma, which is larger than the square root of n if alpha plus beta over 2 minus gamma is bigger than 1/2. So now let's compare the spectral algorithm and the log density framework. So the log density framework succeeds if gamma is less than alpha times beta. The spectral algorithm succeeds if alpha plus beta over 2 minus gamma is bigger than 1/2, which is true if and only if gamma is less than beta over 2 minus 1/2 plus alpha. So subtracting the first bound from the second bound gives beta over 2 minus 1/2 plus alpha times beta, which is equal to, in parentheses, alpha minus 1/2 times 1 minus beta. And this is larger than 0 if and only if alpha is bigger than 1/2. So the spectral algorithm does better than the log density framework when alpha is bigger than 1/2. Okay, so these are the main upper bounds for densest k-subgraph. I'll now describe our sum of squares lower bound for densest k-subgraph. So you likely heard about the sum of squares hierarchy before, but just in case, the sum of squares hierarchy is a powerful model which captures everything which can be proved using polynomial equalities and the fact that squares are non-negative. So a simple example is that x squared minus 4x plus 5 is greater than or equal to 1 for all real x. And we can show this by observing that x squared minus 4x plus 5 is equal to x minus 2 squared plus 1, which is clearly greater than or equal to 1 for all real x. So a very important example is the Cauchy-Schwarz inequality, which says that for all real x1 through xn and y1 through yn, the sum from I equals 1 to n of xi times yi in parentheses squared is at most the sum from I equals 1 to n of xi squared times the sum from I equals 1 to n of yi squared. And so Cauchy-Schwarz can be proved using a sum of squares proof as follows. So why is the sum of squares hierarchy a hierarchy? So the sum of squares hierarchy is parameterized by a degree d, where degree d SOS looks at polynomials up to degree d. As d increases, degree d SOS becomes more powerful, but takes more time to implement. Now, a fundamental question is, how powerful is the sum of squares hierarchy? A partial answer is that SOS is surprisingly powerful and captures much of our mathematical reasoning. In fact, for many optimization problems, SOS is conjectured to be optimal. So the upshot is that SOS is a strong model, and proving SOS lower bounds gives strong evidence of hardness. So now, roughly speaking, our lower bound says that if alpha is at most 1/2 and gamma is larger than alpha times beta, but less than gamma, then degree n to the omega gamma minus alpha times beta SOS cannot distinguish between the random and planted distributions. Note that when alpha is less than or equal to 1/2, this matches the log density framework. So our lower bound gives strong evidence that the log density framework is optimal when alpha is less than or equal to 1/2. So I should note that in concurrent and independent work, Dawan, Mao, and Wine proved low-degree polynomial lower bounds for densest k-subgraph. So here's a rough comparison between our bounds. So low-degree polynomial lower bounds are weaker than SOS lower bounds proved by a pseudo-calibration, which our lower bound is. That said, they prove lower bounds for hypergraphs as well as graphs, and they prove lower bounds for the regime where alpha is bigger than 1/2. So in order to precisely state our lower bound, we'll need to describe densest k-subgraph using polynomial equations. So we can do that as follows. So the idea is that for each vertex I, we have a variable xi, where we want that xi is 1 if I is in the dense subgraph, and xi equals 0 if it's not. So now, in the densest k-subgraph problem, we're trying to maximize the sum over the edges ij and e of g of xi times xj. As this gives the number of edges contained in the subgraph, subject to for all I and n, xi squared equals xi. This says every vertex is either in the subgraph or not in the subgraph. And the sum from I equals 1 to k of xi equals k. This says that the subgraph has size k. So now our precise theorem statement is as follows. For all parameters alpha, beta, gamma between 0 and 1, where alpha is at most 1/2, and gamma is bigger than alpha times beta, but less than beta. There exists a delta bigger than 0, such that if G is a random GNP graph, then with high probability there exists degree n to the delta pseudo expectation values tilde e, such that tilde e of 1 equals 1 plus or minus the lower of 1. The sum over ij and e of g, the pseudo expectation value of xi times xj is approximately k choose 2 times q. So this says like SOS thinks that the planted or that the dense subgraph has roughly k choose 2 times q edges. The sum over I of the pseudo expectation value of xi is approximately k. This says that SOS thinks that there's a dense subgraph that the dense subgraph has size approximately k. And the moment matrix M is PSD. So this condition is needed for the pseudo expectation values to be valid. And if you're familiar with sum of squares, lower bounds, then you'll know that this is by far the toughest condition to check. So I should note 2 things. So first, it turns out that the pseudo expectation value of 1 being 1 plus or minus the lower of 1 fails with inverse polynomial probability. So it turns out that this is related to the fact that there is a distinguisher which with inverse polynomial probability can distinguish these 2 distributions, and namely it looks for a dense subgraph which is unlikely to appear in either case, but is much more unlikely to appear in GNP as opposed to GKQ. But interestingly, even when this fails, M is still PSD with high probability. And so our second note is that we only satisfy the constraint that the sum over I of xi equals k approximately. So as a note, the SOS lower bound for planted clique had the same subtle issue. For planted clique, this issue was resolved by Peng in 2021. Okay, so in the last part of my talk, I'll give a taste of the technical analysis. So for our SOS lower bound, we follow the same general ideas as the SOS lower bound for planted clique. That said, there are several new technical challenges. So first, instead of using leftmost and rightmost minimum vertex separators for decomposing shapes into left, middle, and right parts, we need to use the leftmost and rightmost sparse minimum vertex separators. After finding the Second, after finding the leftmost and rightmost SMVS, we need to split into cases based on whether the corresponding edges are actually in the graph. If they are not, we need to delete these edges and search for new leftmost and rightmost SMVS. We call the resulting SMVS the leftmost and rightmost positive minimum vertex separator. And implementing all this requires a new analysis for middle shapes and new intersection trade-off values. Okay, so that was a mouthful, and that probably didn't make much sense unless you're a sum of squares lower bounds expert. So instead of discussing these challenges, I'll show the analysis for middle shapes, which is the easiest part of the analysis. And I'll show how the conditions that alpha is less than or equal to 1/2 and gamma is bigger than alpha times beta arise from this analysis. For this analysis, I'll show the steps of the analysis, but I won't be able to fully explain why we take these steps. So in our analysis, we work with objects called shapes, where a shape alpha consists of a graph with distinguished tuples of vertices u alpha and v alpha, which we call the left and right sides of alpha. So here's an example shape alpha. So in our analysis, each shape has a coefficient and a norm bound. The coefficient of a shape alpha is lambda alpha equals n to the alpha minus 1 times the number of vertices of alpha, plus beta over 2 minus gamma times the number of edges of alpha. For example, for this shape alpha, its coefficient is n to the 7 times alpha minus 1 plus 6 times beta over 2 minus gamma. So as a note, this coefficient comes from the way we construct the pseudo-expectation values tilde e using the pseudo-calibration technique Barak et al. So I'll now need to define the sparse minimum vertex separators. So given a set of vertices S, we define the weight WS of S to be WS equals the size of S minus beta times the number of edges in S. Yeah, so there's a here E of S is the set of edges between vertices of S. We say that S is a vertex separator of a shape alpha if all paths from U alpha to V alpha, including paths of length 0, contain at least one vertex of S. So given a shape alpha, we define a sparse minimum vertex separator, which we abbreviate as SMVS, to be a vertex separator S such that the weight of S is minimized. So here are some examples. So if we consider our example shape alpha, so then if beta is less than or equal to 1/2, then for example the blue vertices shown on the left separate U alpha and V alpha and have weight 2, which is the minimum possible weight. So they're an example of an SMVS, though there are other SMVS here. On the other hand, if beta is bigger than 1/2, then the 3 middle vertices shown in red on the right are the unique SMVS. So now, in our analysis, each shape alpha describes a graph matrix M alpha. So there are rough norm bounds on these graph matrices, which are as follows. For all shapes alpha, with high probability, the norm of M alpha is O tilde of n to the number of vertices in alpha minus the weight of a minimum SMVS S of alpha divided by 2. So for example, for the shape alpha, for our example shape alpha, if beta is at most 1/2, then the 2 vertices on the left are an SMVS. So with high probability, the norm of M alpha is O tilde of n to the 7 minus 2 over 2, which is O tilde of n to the 5/2. If beta is larger than 1/2, then with high probability, the norm of M alpha is O tilde of n to the 7 minus, in parentheses, 3 minus 2 beta, all that divided by 2, which is O tilde of n to the 2 plus beta. So as a second example, if we look at this shape on the right, so here the SMVS is the vertex in the middle. So here, with high probability, the norm of M alpha 2 is O tilde of n to the 5 minus 1 over 2, which is O tilde of n squared. So in order to give the analysis, I need to define two more things. So I need to define the identity shape IDU and middle shapes. So given a set of vertices U, which may have some edges between them, we define the identity shape IDU to be the shape with VIDU equals U, EIDU is the edges is E of U, the set of edges between vertices of U, and UIDU equals VIDU equals U. So here's a picture of the shape IDU, and then it's not hard to show that with high probability, the norm of MIDU is O tilde of n to the beta times the number of edges in U divided by 2. So now a middle shape is a shape tau such that both U tau and V tau are an SMVS for tau. So if we look at the four shapes shown below, so here alpha 2 and IDU are middle shapes, as both the blue vertices and the purple vertices are an SMVS. On the other hand, alpha z is not a middle shape, as the red vertices shown, which are the endpoints of the diagonal edge, are the unique SMVS. And alpha is a middle shape if and only if beta is at most 1/2. So now I can give the analysis for middle shapes. For the PSD&ES analysis, we want to have that the middle shapes are dominated by the identity. In particular, we want to have that for all middle shapes tau which are not the identity, lambda tau times the norm of m tau is much less than lambda IDU tau times the norm of m IDU tau. So for this, we need to have that n to the alpha minus 1 times the number of vertices in tau plus beta over 2 minus gamma times the number of edges of tau. So this comes from the coefficient lambda tau for tau, plus v tau minus the weight of u tau over 2. This comes from the norm of m tau. Note that u tau, since tau is a middle shape, u tau is an SMVS for tau. We need to have that this is much less than n to the alpha minus 1 times the number of vertices in u tau plus beta over 2 minus gamma times the number of edges in u tau. So this part comes from the coefficient for ID u tau. And then plus the number of vertices in u tau minus the weight of u tau over 2. And this comes from the norm bound on MID u tau. So this is true if alpha minus 1/2 times, in parentheses, the number of vertices in tau minus the number of vertices in u tau, plus beta over 2 minus gamma times the number of vertices in tau minus the number of edges in u tau. So this is true if all of this is less than 0. So we need that this inequality holds. So now observe that if we just look at the terms for v tau and e tau, so if we subtract and add alpha beta minus beta over 2 times e tau, so then this blue part is equal to alpha minus 1/2 times, in parentheses, the number of vertices in tau minus beta times the number of edges in tau, which is equal to alpha minus 1/2 times the weight of tau. And then this purple part is minus, in parentheses, gamma minus alpha beta times the number of edges of tau. Following similar logic, alpha minus 1/2 times number of vertices in u tau plus beta over 2 minus gamma times the number of edges in u tau is equal to alpha minus 1/2 times the weight of u tau minus, in parentheses, gamma minus alpha beta times the number of edges in u tau. So now the key observation is as follows. Since tau is a middle shape, the weight of tau is greater than or equal to the weight of u tau. Since alpha is at most 1/2 and gamma is bigger than alpha times beta. So now our expression at the top, we can rewrite it as alpha minus 1/2 times, in parentheses, the weight of tau minus the weight of u tau, minus gamma minus alpha beta times, in parentheses, the number of edges of tau minus the number of edges of u tau. So now, since tau is a middle shape, the weight of tau is greater than or equal to the weight of u tau. And since alpha is less than or equal to 1/2, this first term is less than or equal to 0. And then since gamma is bigger than alpha times beta, the second term is less than 0. So this entire expression, if these conditions hold, this entire expression is less than 0. And this shows how the conditions that alpha is at most 1/2 and gamma is larger than alpha times beta arise from the analysis. So I'll end here. Thank you for your attention.